Hello, this is Mr. Bush, and what we're going over today is a real quick review over last week. So first off, we're going to go over the theory of continental drift, and this is that at one time all the continents were connected in a supercontinent known as Pangaea, and then over time these continents had drifted apart. So let's go ahead and review some of the evidence to support that. Well, the four biggest pieces of evidence to support that the continents were once connected is, first off, their shape. You can kind of see that all the continents almost fit together as if there was a jigsaw puzzle. Now, the next one is, if you look at the fossil records, we had a large group of fossils found all the way across all of our continents. So, if you look here, like this animal here, couldn't have swam, but it was found across 3 different continents in this sort of band pattern. What that meant was, since they couldn't swim, they couldn't fly, at one point all of these continents had to be connected together so they could basically walk across to each other. Alright. The next piece of evidence is some of the plant fossils we found in Antarctica. If you look here, this plant was found in the continent of Antarctica. It's strictly a tropical plant, which means it only grew in warm weather. So if it was growing in Antarctica, that means that Antarctica had to be warm at some point. And the only way for Antarctica to be warm was if it was in a different location closer to the equator. Alright, let's go ahead and look at our last 2 pieces of evidence. Alright, rock types found across South America and Africa basically pair up, indicating at one point they were basically connected. And the same thing for Australia, Antarctica, and India. And the last one is there's certain mountain ranges like the Appalachian and the Greenland Mountains and the Atlas Mountains that basically all share the same type of rocks, same age, that sort of thing, indicating at one point they were all connected. Alright, let's go ahead and look on how they moved. Now, the next thing we learned about is how the continents actually moved. And basically the force that's providing them to move is going to be convection currents flowing in the mantle underneath the plates. So if you look here, basically these circular patterns of melted rock or magma going in a circle, that's going to pull these plates along. Now, as they bump into each other, either one, the more denser plate often slides underneath the other, and it really doesn't happen very fast. They move maybe about an inch or 2 a year. So the convection currents are the ones that are providing the force to basically move our large continental plates. Let's go ahead and look at this from a different angle. So once again, keeping in mind with Newton's first law, or the law of inertia, these plates won't move without a force pushing them. You have our convection currents in the mantle. Think of it like a boat floating on a river. As these currents move, it basically causes, as these currents move, the plates kind of float along and are pushed along by the currents. So it's basically like a little boat floating on a river. Alright, let's go ahead and look at our different types of boundaries. Alright, any place where these tectonic plates touch, it's going to be called a boundary. Kind of like the boundary of a country or a state. It's just where these 2 plates meet. Now there's 3 main types. Divergent means the plates are moving away from each other. So if you look right here, our divergent plates, they have the 2 plates pulling away from each other. Convergent, you're going to have the 2 plates basically being pushed together. Alright, and this is basically, you're going to have 2 large plates moving in together, and it kind of basically, just if you get confused, think of what the word actually means. Converge means to come together, like when 2 roads converge, it means the 2 roads are coming together. Now the last one is going to be transforming, and it's when they basically move sideways to each other. So like you have them, they're moving in opposite directions and they're basically sliding against each other. So this is good. The last one is going to be transforming, and it's when we have our plates sliding against each other. Alright, the last thing we're going to look at is going to be seafloor spreading and a subduction zone. Alright, a subduction zone is basically where one plate slides underneath the other. So if you look right here, you have this plate sliding underneath our continental plate, and that's going to be a subduction zone. So it's where you have two converging plates, one slides underneath the other, and that will form a subduction zone. Now here's one part where some of my students got confused on Friday. You can have a converging boundary and a subduction zone in the same area. Basically, converging boundaries will often cause a subduction zone. So don't think that it's either a subduction zone or a converging boundary. Often converging boundaries make a subduction zone. Alright, let's go ahead and look at our seafloor spreading. Alright, seafloor spreading occurs when two oceanic plates are diverging. So they're basically created by a divergent boundary underneath the ocean. These two plates are going to pull away from each other, and what happens is some of the lava comes up and it creates new rock. So basically when the lava comes up in the form of volcanoes and vents, it hardens and it forms new rock for the basically that large tectonic plate. Now your newest rock is going to be very close to the boundary. Your oldest rock is going to be over here towards the edges of the of that plate, because the newest rock is formed here, and as it moves along, basically you have older and older rock being pushed out to the edges. Alright, that's all for today, and hopefully this was helpful.